start with an introduction. How many people were at my presentation yesterday, Qt in Depth? Okay, about half of you. For those of you that that weren't there, my name is Brad Hughes. My full name is Bradley Tyson Hughes. It looks nice, and my mom's proud when I use my full name, so I figured I'd do that here as well. I am a senior software developer for Trolltech ASA based in Oslo, Norway. I work at the headquarters. I moved there about 6.5 years ago from a small town in Texas called Amarillo. If anybody has ever been to Amarillo, Texas, which I seriously doubt. I was recently appointed as the leader of the Qt platform team. This is actually a pretty funny story. Everybody remembers Matthias from the keynote yesterday. He has opened up a new office in Berlin. And the Friday before he goes down to Berlin to open up the new office, he comes into my office and says, how do you view your role in the company? That's not the type of question you want to get from your boss, is it? It makes you feel about that big. Of course, the people that were at my presentation yesterday, they've heard all of this. But anyway, he wanted to make me feel bad for a quick second just because that's the way he is. And he asked me if I would mind taking over some of the platform-specific parts of Qt. This involves the X11 parts, which I'd already been maintaining, and kind of taking over responsibility for the Windows, the Mac ports, and a lot of the kernel parts, the signals and slots, the QObject, parent-child relationships, all the things that we provide, in addition to the threading and a lot of the other things that I'd been doing. And of course, I said yes. It's basically a promotion, so why not, right? I got a couple of guys that work together with me, and we're called the platform team. So, it's a funny story. I love telling it. Because also, too, I get to do an impression of Matthias. But, it's not a great one, I know. Before I worked at Trolltech, I did quite a bit of, well, not quite a bit. I come from the open source community. I'd written a window manager called Blackbox for X11. Actually, is quite flattering to people at the cocktail party here a couple evenings ago, where I could see people talking over their shoulder, pointing at me. It's like, oh yeah, he's the Blackbox guy. So yeah, so that's a little bit about me. Before then, I had done little odd jobs. I had worked and sold shoes and eyeglasses and these types of things in school, but it's not important here, right? But yeah, that's enough about me. Why are we here? We're going to talk about how to take your application and start developing on Linux. I'm assuming that most of the people here are familiar with development on Windows already. So a lot of the topics we're going to cover are Linux specific, and I'm going to compare them with the Windows equivalents. This is kind of an introduction, a bit of an intermediate level, maybe more on the basic side, just to kind of, jumpstart, get you started on how can I get my application over on Linux, right? We're going to talk about a couple of different things. Talk about the different IDEs that are available on Linux. We're going to go dig a little deeper into the compiler, the tool chain, the linker, the assembler, all of those things. The debugging tools, profiling tools, and at the end, as both Matthias and Benoit have pointed out, the development on Linux, people tend to use something like VI or Emacs or these types of things, and we'll cover those at the end. I don't want to scare you from the beginning. So that's the reason I put IDEs as the first topic I wanted to talk about. Developing on Linux is really not that scary. It's not that difficult. There are things you have to kind of watch out for. Things like path separators are different. They're normal slashes instead of backslashes. These types of things. The Qt API insulates you from a lot of the platform-specific parts. So apart from things like drives and path separators, you really don't have to worry too much about those types of things. When you get ready to deploy your application, I recommend you go and either, I don't know if it's already over, may have already been, the deployment presentation that Harold gave. If you didn't get a chance to catch that, maybe watch the video once it becomes available. It kind of describes how you can get your application that you've now developed on Linux into a package that you can then deliver to your customers. I'm not going to talk about that here. I'm just going to talk about development. Development on Linux, right? Like I say, not too different, very similar. Don't have to be scared about that. The easiest thing for you to do is just start using an IDE. There are several of them that are available. Many of them are very similar to Microsoft Visual Studio, if you've used that before. Eclipse is also available on Linux, which is identical to what you would use on Windows if you use that on Windows, of course. The whole reason we use IDEs, right, this is an environment. It pulls everything together. We can use the compiler and the debugger and all of these tools from one environment. And just more convenient that way, right? I have a feeling these screenshots are going to be quite ugly. Yes, they are. This is one of the more well-known IDEs called KDevelop. Right? And this is a KDE development tool that integrates very nicely with the Qt build system, the Qt API. You can read the Qt documentation directly from KDevelop. It's a nice tool. We have quite a few people at Trolltech that actually use it. Supports lots of nice features, things like syntax highlighting and code completion, these types of things that you find in Visual Studio as well. It offers project management. If you use QMake project profiles, you can also edit these and manage these from KDevelop, which is actually kind of nice. Something that I think the Visual Studio integration has, actually. So if you use that, you can also do it here. And as I mentioned, the whole point of the IDE, right? Integrate the compiler, documentation, debugger, and even revision control. If you use things like CVS or Subversion or Perforce, like what we do, the KDevelop can give you these things as well. Eclipse, everybody's probably seen this before, provides a lot of the same things. Syntax highlighting, code completion, and all of the debugger integration. Has some nice things that KDevelop doesn't have. It has a full C++ parser, so and I believe it actually does compiling in the background, sort of the similar way it does with Java. So it'll build your projects for you kind of on the fly, which is neat. Those are the two IDEs that are mostly used on Linux. There are lots of others. It's like cars. Everybody likes to drive a different car. Well, everybody also likes to use a different IDE. Pick the one that works the best for you. But if you do use one of those, the moving to development on Linux won't be too hard. So the real meat of the presentation now, right? Let's talk about the different development tools. So we'll start with the compiler and the tool chain. Most people on Linux use the GCC, the GNU compiler collection. This is a collection of C, C++, Java, Ada, Fortran, and several other languages. I'm going to talk about GCC and G++, because those are the two that you would use for doing Qt development. GCC builds on top of something called bin utils. This is also a GNU project. This is a collection of tools to do assembly. The linker is part of bin utils. And there are also other tools like R to create static library archives, OBJDump, which is a disassembler and generic object file inspector. OBJDump is actually quite hard to use, but it's very useful, especially if you want to look at disassembly or do post-mortem debugging. You want to debug something after an application has crashed. These things help quite a bit. There are many more. I don't want to cover them here. Some of them are more obscure. But if you read the bin utils documentation, you can get into some of the other tools that are very similar to the ones we're going to mention here. Next thing, GCC. How does it work? Right. GCC is a little different from the way Visual Studio works. GCC is just a compiler. It doesn't generate any object code. It only compiles to assembly. So what GCC does, it will take your code, run the preprocessor over it, and then pass that off to compile it to assembler. And then it passes that assembler to the assembly output to bin utils, which will then assemble it and generate the object code. This is the way GCC works. A little different from the Microsoft compiler. The assembler step is part of the compile process. You don't have to do it yourself, but I just wanted to show how it actually works. You can tell GCC that I want to compile to assembler only. Don't generate the object code. So if you're a bit crazy like I am, sometimes you like to look at the assembler output. GCC lets you do that. You don't have to do that yet. It's interesting reads, though. It really is. Some of the other differences between GCC and the Microsoft compiler. The .NET 2002 and up to the recent 2005 releases, they're all compliant with the C++ standard, just like GCC is. So if your code is, if you compile your code with one of these compilers already, you shouldn't have too many problems moving to GCC. If you're using the Microsoft Visual Studio 6 compiler, there are a few minor differences that you'll have to watch out for when moving to GCC. The Microsoft 6.0 compiler actually supports a draft of the C++ standard. I think I mentioned this yesterday. They released MSVC 6 on September 1st of 1998, whereas the C++ standard first edition was released on September 2nd of 1998. So I can guarantee you they didn't fix they didn't fix the compiler to adopt some of the changes that are in the final standard. So Microsoft Visual Studio 6, some of the code that it accepts will not be accepted like GCC. One very common example that you run into is for scoping. Variables that you declare in the for loop will be accessible outside of the for loop. GCC adheres to the C++ standard rules and does not allow this to be accepted. It will not accept this code. So certain things to watch out for. But these types of things they're easy to get over, right? The command line options to GCC are much different from from the Microsoft compilers. Most people don't have to touch these, but they're nice to know, right? By default, GCC will try to compile and link your application. So GCC has a flag -C, which tells the compiler to only generate an object file. Don't actually try to link libraries and make an executable. Just create an object file that I can link into my target later. Generate debug info, optimize the code. You can actually use these together. People do this quite often. And various other options. Write my output to a file. I want to have different include paths or different defines. These are very similar to the Microsoft compiler. Some of the more advanced C++ features that are optional in the Microsoft compiler, which you have to turn on explicitly, are enabled by default in GCC. Exceptions, RTTI support specifically. There are flags to turn them off if you don't want them. You can -F, no exceptions, -F, no RTTI to disable those if you don't need them and if you don't want them. Why you would do that, I don't really know. Earlier versions of GCC, it paid off to turn off the exception support. Newer versions implement exceptions in a much cleaner way, so you can leave this on even if you don't use exceptions. You don't get any kind of code performance penalties, and the code size is not that much larger. So, but for completeness, there it is. This is one difference between GCC and the Microsoft compiler. Right? GCC is used also for linking. As I mentioned, it will try to link your application by default. This is different from the Microsoft toolchain, where you have a separate tool to generate your executables in your libraries. On Linux, you'll use GCC to do this. You can use LD directly, but it's a bit complicated. You have to know where certain startup files would be, how to find all of the various libraries, these types of things. GCC gives you some nice options to do that automatically. You can give it paths to look, give it a directory to look in to find library files. And the -l followed by the name of the library, it means link this library into my application. This works both for shared libraries and for static libraries. So it just works. You don't have to know it beforehand if these are shared or static libraries. One difference, though, as you see here, on Linux, the convention is not to have a separate debug library like you do in the Microsoft world. The runtimes are very often compiled with both the -G and the -O2, both with the flags to generate debug information and to optimize the code. This is just the way it's done. If you go and download code that you want to compile yourself on Linux, many of them will use a configure script that by default will use these as well. This is just a convention that's been adopted by many software packages. So we've actually started to do this as well in Qt 4.2. So, small example, right? First two lines compile two different files, and the last one links, right? So what does it say here? I've got my notes, so I don't have to keep looking up there. First line compiles A.cpp, second line compiles B.cpp, slightly different compiler flags, and then the last one links the application with -lazy. What is that? Well, as you can see, -l AZY, right? You'll see tricks like this. People, it's nice to have a little bit of fun, right? -lazy, the GNU project, the people that make GCC, they have a library called libiberty. So whenever they link GCC, the final link line looks like, -o GCC, and the final library that they link is -l liberty. The FreeBSD project has a library called libegacy. So they have a library called, when they link, they have -legacy. So it's kind of fun. So I figured I'd show that, right? Have to have a little fun. It's software development. So there is really no -lazy flag. It means link with a library called libazy. Right. Make is the common build tool on Linux. This is something that you rarely call the compiler directly, just like with the Microsoft toolchain. You very rarely call the compiler directly. You usually use something to automate the build for you. Here you can see an example of a very simple make file. Right? You define rules. The rule is the first thing you see in a file, followed by a colon, and then a dependency list afterwards. On the next line, a tab character, and then the name of the command to actually build the target that's named. This is the Microsoft nmake tool uses the same syntax. Right? So if you're familiar with that, this is identical. Just we use different commands here, right? But of course, if you're going to be developing with Qt, you probably want to use QMake, right? QMake can create the make file for you on Linux. It can create a project file for you on Windows. So use a project file. It's much easier. It'll generate the things you need on the correct platform for you. And yeah, if you're not using it, you really should give it a try. It'll save you a lot of headache. Writing make files by hand is not fun, speaking from experience. So that's a small introduction to the compiler and the toolchain, right? Once you've got your application built, next thing you need to do is debug it, right? All software has bugs, even Qt, I have to admit it, yes. So let's talk about the debugger. Again, from the GNU project, GDB. This is an open source tool just like the others. This is a command line debugger. Whenever you use GDB, you get to go to the command line and use it from there. There are GUI frontends available, and many of the IDEs will integrate very nicely with GDB. Some of them will actually allow you to use pointy, clicky commands or give you a command line interface, your choice. You can use either. And of course, GDB is a full-blown debugger. It supports both runtime debugging. You can set breakpoints and examine data while the application is running, or you can do post-mortem debugging after your application has crashed. You can go in, load something called a core file. When your program crashes, it will usually generate something called a core file on disk. You can use GDB to go through and examine the data that was in the memory space of your application when it crashed. So, very useful tool. Yeah, I'm getting ahead of myself, aren't I? Right, like I said, you can set breakpoints. This means run your application in the debugger. You can examine data on the stack, in the heap. You can set hardware watch points. These are actually very useful. You can watch an address in memory, and whenever that address changes, GDB can break the program and allow you to examine what happened when something in memory changed, not just a normal breakpoint, right? And of course, GDB also has thread support, just like you would expect. Starting GDB is very straightforward. Just run GDB and give it the name of the program you want to debug. The third argument is optional. You can either give it the name of the core file, right? This is the memory image that is dumped to disk whenever your program crashes. Or you can also give it a process ID number, which means it will attach to a running process that you've already started outside of the debugger. And you can then start debugging the application while it's running. So this is actually very useful, especially if you want to debug something that has been in an application that's been running for a very long time, right? If it's very hard to reproduce, these types of things. The common commands that you'll use in GDB, here are some of them. There's quite a few of them. GDB has lots and lots and lots of commands. It does have online help built into it. You simply type help and you can go through all the options. But I'm going to give you a quick shortcut there's a couple of quick things to get you started so that you don't have to go dig through all that documentation. Run, the command run will run your program if it's not already running, of course. Control-C, the normal interrupt combination, is used to break the program, which means you can then start looking at data, finding out what's going on in your program. Once you've broken your program, you can use commands like BT, which stands for backtrace, or where. They're both the same command. It shows you a backtrace. What's the current function that's being called? What are the callers? How many functions deep have I called? This will also allow you to look at the arguments that have been passed to a particular function as well. Look, what are the values of various arguments? While you're looking at these functions, you can use the list command to actually show the source code. What is this function doing? You can use list, so you don't have to go back to the editor. You can use list to show you where in the source code am I. And then when you're ready to begin executing again, you can step over statements using next. You can step into statements using step. And you can use continue to just simply return execution or continue execution of the program. Some of the other commands. Break sets a breakpoint. You can use break with no arguments, which will set a breakpoint at the current location. You can set say break on in a file and a line number. You can also say break on an address, which you rarely do, but it's possible to do. You can say break on an address, which happens to match the address where your code is loaded into memory. You very, very rarely use that, but you can do it. Print will print the value of a variable. GDB supports the standard C syntax, so you can actually dereference values. You can take the address of things. You can cast things to different types, and GDB will do the right thing and print out the correct value. The frame command will allow you to jump from different calling frames, between calling frames. If you want to look at usually frame 0 is main, where your program begins execution, and you can use frame to jump between callers and callees of the current function you're examining. And then a nice command that I actually learned here not too long ago, a command called finish. This means run the current function until it returns. This is usually very handy. I've been using GDB for years. I never knew about that until this summer. So use it. It's actually very, very handy. And as I mentioned, GDB does have support for debugging multi-threaded programs, so you can use the command info threads. It will show you a list of the current executing threads in your program, and you can use the thread command to jump between these threads. You can examine the stack and the data for each of these individual threads by just simply switching between them. So just to kind of give you an idea of how this works, figured I'd do a quick little walkthrough. Right. In bold is the command that we're going to be executing, and then the rest is the output that GDB gives you. So I'm going to debug the semaphores example. This doesn't have any bugs placed into it. I'm just going to show how the commands are used. So we're not actually going to fix a bug. We're just going to run the program through the debugger. Right. So start the debugger, GDB, the name of the executable. GDB tells me its version, its copyright information, and then a whole bunch of other licensing stuff. I've elided that because I didn't have space. There's a lot of it. But after all that, GDB gives you a prompt, right? So we're going to set a breakpoint, right? We can use the break command. Say, I want to break in the function main. It will tell you, okay, I'm going to break at function name. Gives you the address of that function. Like I said, you can, just in case it's useful, it's probably not, but it can be. Tells you what file and what line number that breakpoint is also set in. Right? GDB knows all this stuff, just like this. So you can go in and examine the code later, right? Run the command. Yep, tells me it's running. You can see this is a threaded program, so it has to load in a special library to enable debugging the threads. So it's telling me it's doing that. Very verbose. A new thread to execute main is created, and then execution starts. First thing that happens, of course, is it's going to tell me, hey, you've hit a breakpoint. We've just come into main. So switches to the thread that was just created and says, we've now hit breakpoint 1. You can see we get arguments with their values, line number, location, and then the line of code that will be executed next is shown. Right? So we use the BT command, right? There's only one frame. We've just come into main, so that's the only frame that we see in the stack trace. So, moving on. Let's use next. We're going to step over and execute the Q application constructor. Okay, it does that. It says now we're at line 61. This is something called producer. What is that? Let's see what it does. We step into the constructor of producer using step. It tells me, okay, we're going to create producer. Here's the address that producer is going to be created at. Shows us this pointer, line number, and all that good stuff. But okay, the curly brace, what is that? Well, the compiler generates a default constructor for everything, right? Any class, even if it doesn't have a constructor, the compiler will generate one for you. If we look at the code, this particular class doesn't have one, so we've actually stepped into this default constructor that the compiler has generated for us. Right? That's what we see here. So sometimes you may see execution or the next instruction is some sort of curly brace or some sort of statement that you don't expect. A lot of times this may be because the compiler has injected code for you that you didn't explicitly write. That's the case that has happened here. So this is a function that I know nothing about. I just want to let it do its job, so I use finish, right? Lovely command. I can't believe I went 5 years without ever knowing that. Anyway, so finish, we go back to the main function. Line 62 is the next line. We're going to create a consumer. Hey, everybody's done producer consumer before, right? Yeah, I think so. So, okay, we'll create a consumer. Consumer is the same way as producer. It doesn't have a constructor, so I'm not going to step into it. I'm just going to go over it. The next statement after that is start. We're going to start a thread. That's interesting. I want to see what happens in these threads. So I'm going to set some breakpoints. I'm going to set the breakpoints in my run implementations of these two threads. So I set these two breakpoints. GDB tells me where they are. And now I'm going to let the program continue. I'm going to wait until it breaks in these two threads. So since producer start was the next statement, it's right after we say continue, we get another breakpoint. We're breaking in producer run. We can see the first line of run. This will be the next statement that's executed. It's going to seed a random number. For those of you that didn't know, the semaphores example actually generates a random DNA sequence. So it has to seed the random number generator, right? If you look at the stack trace, right, this is I'll go back, right? Some of these this cryptic output up at the top. When we typed continue, the next statement was to start the producer thread. So GDB tells us a new thread has been created. And when we hit the breakpoint, we've now switched to that thread. And we've stopped execution. The current thread is this new thread that's just been started. And we can now look at the backtrace for that thread, right? We're not in main. This is, right, we're in producer run. Under that, you see some of the internal stuff that we do to start a thread, right? And some stuff that comes out of libc because we build on top of the libc parts, the pthread API. So that's what the stack trace is usually going to look like in your threads. If we look at what, we at this point in time, we really only have two threads, right? We have the thread running the producer and then the thread running main. Thread 1 is currently, you can see thread 2. This is where we are now. Thread 2 is stopped. This is the current thread. You can see the star that indicates that. And it's stopped at line 34, semaphores.cpp. That's what we would expect. Thread 1, it's off creating the consumer at the moment. So I don't know where it is. It's in something called clone. So let's let it finish doing what it's doing, right? Finishes creating that thread, switches to thread 3. This is the consumer thread. Breakpoint. Here we are. We're in semaphores.cpp line 50, consumer run. And then the first line of code for the consumer. Stack trace here looks very much like the producer, right? Except this is the consumer thread, not the producer thread. Stack trace under the frame 0 looks identical to the producer because that's the implementation detail that we've done for you, right? But now we have 3 threads running, right? We have thread 1, 2, and 3. Current thread is number 3, and you see the thread 1 and 2 are waiting on something. They're actually waiting on the consumer, believe it or not, right? If we need to, we can switch between these different threads. We can switch back to thread 2. We see, oh, it's in some pthread wait function. What has called that wait function? Well, that's QSemaphore that has actually done that. QSemaphore actually uses QWait condition internally, which is calling pthread called wait. And then there you see that was actually called from producer run. Producer is waiting for the consumer to consume something before it can produce more. Yeah, exciting, isn't it? If we switch back to thread 3, very simple. GDB shows us where we are. and we can examine the use thread, switch between them. We can look at the stack of what's going on. So, like I said, I'm not going to actually, there's no bugs or anything in this one. I'm just showing you how to use the debugger. I haven't printed any variables or tried to actually use any of the other commands. I'm just showing you this is how you can debug a program. Also, a threaded program. So, normally, when you just run your application and everything works okay, you'll see all the threads exit and the program quits. So, we're going to quit GDB as well. Right? Like I said, it's just a kind of an introduction how you can use GDB. The next tool is the one that we use the most at Trolltech. GDB is useful, but only to a certain degree. Valgrind, the next thing I want to talk about, is a very useful tool. 10 minutes. Wow, okay. I need to speed up. Valgrind is a tool about, this is a debugging tool. It is based on top of CPU simulation. What it does is it takes your application and runs it in a virtual machine. And there are various tools, like kind of plugins for Valgrind. What they will do is they will go through and examine what your program is doing and tell you whenever something is going wrong or if it's detected some sort of potential problem. Valgrind comes with debugging and profiling tools as well as code coverage tools to kind of give you an idea of, this gives you an idea of what you can do with it. Right? You can use debugging, you can do profiling, you can also do code coverage. See, for example, we use the code coverage tool to see how much functionality we actually test in our testing framework. It's a very useful thing. The default tool in Valgrind is called memcheck. What this does is detect memory problems. It looks at things like got it here, uninitialized memory. If you try to read or write to an uninitialized piece of memory, well, writing is not so much a problem. Reading it is a problem. If you read or write data that has recently been freed, Valgrind can tell you about that. If you do out-of-bounds reads or writes, right, you write a byte before or after a piece of memory, Valgrind will also tell you about that. It can also tell you about memory leaks. It tracks all the allocations that happen in your program. It can tell you whether or not something has leaked. It's not been freed. And it can also tell you about things like mismatched new and deletes, or array new and array delete, or malloc and free, right? You don't want to mix new and free or malloc and delete. You want to make sure that you use the same ones. Valgrind can tell you about those. I got a nice little small example, little program to print out to make a copy of my name, right? Obvious problem, I don't have enough space, do I? So, compile my program and I run it through Valgrind. The default tool in Valgrind is memcheck. You don't have to have the -- tool equals memcheck, but I do it for completeness here, right? So Valgrind tells me, starts up, has, just like GDB, for some reason they love to tell me that I can use them under the GPL. So I've not put that here. I don't have the space. But here you can see an example. I've written 1 byte after the end of a memory block, so Valgrind tells me about it. Tells me where this happened, because I've compiled my program with debug information enabled, right? You definitely want to do that. Valgrind can tell you this particular piece of memory was allocated at this spot, and it was incorrectly used at that spot. Gives you the address and also tells you it was 0 bytes, or maybe 10 bytes, or 12 bytes before or after a particular block of memory. Right? Once a program exits, it will tell you there is a certain number of errors. It will tell you how many allocations and how many deallocations your program made during its life. And it also tells you a leak summary, how much memory was actually in use when your program exited. In my case, I had 4 bytes. that were definitely lost. Definitely lost. What does this mean, right? We see this definitely lost, possibly lost, still reachable, and suppressed. Suppressed is suppressed. You're not going to see them. Definitely lost means that this particular piece of memory that was not freed, Valgrind looks through your program and tries to find a pointer that points at that block of memory. If it can't find one, that is definitely lost, right? In my particular program, I had a local pointer in the main function pointing to my block of memory. When main returns, I have no pointer to that memory. Definitely lost. Possibly lost means you've got a pointer to the inside of your memory block. This is very common if you do iteration, copies of a string, right? You have some sort of pointer that points inside of a memory block. If you exit the program with a pointer pointing to the end or the middle of some memory block, Valgrind says, well, that might have been leaked, possibly lost. Still reachable means that pointer is pointing at the beginning of that memory block, right? So you've got a pointer somewhere. Maybe you do some sort of lazy initialization and forgot to clean it up. We've done that before. So that's still reachable. A tip. You can use another flag called leak check. You set it to full, and it will tell you where a particular piece of memory was actually allocated. So after the leak summary, it will give you all of the blocks that were leaked and where they were leaked from. This is what you see here. Of course, you have to also, like I said, you have to compile with debug information to get this type of information. I've got 5 minutes left, so I'm going to have to blow through the profiler. The profiler is actually fairly easy to use. GCC has profiling support built into it, but it has a number of limitations. You have to compile your program with a special flag, and it has to be compiled statically. Yeah, I see this. I see the same expression out in the audience. So we don't use this. You can't profile shared libraries, and it's a bit of a pain. You have to change your build system. So this is where Valgrind steps in. Valgrind works a lot like Purify does. It runs your program in simulation and examines what's going on. You can use something called Valgrind instead of memcheck, and it will actually profile your code, find out where cache misses and these types of things happen, and it will also find out how much does a particular instruction take. Can calculate of all this stuff, and it dumps a file into the current directory that with all of that information, how profiles your application. How much time did it spend executing individual functions? You run it just like you did before with memcheck. You just replace the tool name. You get it, run your application, and when it exits, it spits out some output. I don't know what that means. I will be honest. The file that it generates as well is not human readable as well. You want to use a tool. We use Valgrind to visualize this data. It's a big text file that you can try to interpret, but you won't be able to. So Valgrind, we use that. Shows you how many times the function was called, how much time was spent in that function, and how much time was spent in the calling function, for example. Gives you a nice graph that you can actually export to an image or to PostScript if you want to print it out and see it on paper. This is what it looks like. I profiled that little buggy program of mine, right? Here you can see the call graph. A nice little graph. And here's a detailed view of it. You can see all the functions that were called in my program, how many times they were called, how much time each function took, and how much time each function, including its caller, took in percentage. You can change it to give it to you in the number of instructions as well if you want that. And then here up on the top, you can also see in the code how much time was spent on each individual instruction in a particular function, right? All of the time in this particular function was spent in memory allocation. right? Very useful tool. The profiler is something we use all the time. It's extremely easy to use because it visualizes where the hotspots are in your program. It's a very, very useful tool. I know I'm running out of time. I can cover some of the editors that are available, or we can do questions and answers. Mention them? Sure. Mostly. Is that right? I'm relying on her. So yes, I have a half an hour. She warned me about this. The French, they have no concept of time, right? So we have lots of time to talk about editors, right? So that's good, because the great thing about editors is it's like standards. There's so many to choose from, right? So I'm an Emacs user, so I have to talk about that one first, right? Xemacs is what I use. Some people use GNU Emacs. That's just a matter of taste. For example, Gunnar, he uses GNU Emacs on Windows, no less. A rare breed indeed. Emacs is, it's pretty decent. It supports syntax highlighting. It allows you to run the compiler and make and these types of things within another window. You can actually click on some of the warnings and errors that it points out, and it will jump back into the source code for you. Right? It's pretty nice. You can run the debugger from inside of Emacs, which it's no different from running it from the command line. It just happens to show you have to use the command line function. The command line. You have to use the commands, just like you would on the command line. Sorry. But it also shows you whenever a breakpoint is hit, and as you step through the code, it shows you in the code as well, highlights the lines where it's at, these types of things. So it's not too bad. And the great thing is I have to disagree with Benoit. Lisp is actually a good thing. You can actually customize this thing to do whatever you want. One of the things that Perforce, I don't know if the Perforce guys actually did it themselves or if someone else has done it. The revision control system that we use is actually integrated into Emacs. So I can submit code into the repository directly from Emacs. I can look at differences. I can look at the history and annotations and all these things from inside Emacs. It's a wonderful thing, right? Lisp is not a bad thing. I never learned it, though. I just know it's a good thing because Emacs uses it, right? I don't use VI. Many people do. I don't even know how to use Vim. I can use VI, but I can't use Vim. So I had to steal the screenshot from the Vim website. This is Vim. It's very similar to Emacs and the other IDEs. It does syntax highlighting. You can run the compiler in it. It shows you when you can, on an error, it'll jump you back into the source code where errors and warnings occur, these types of things. So, and I know that people also use the debugger from within VI as well. Customizable, just like Emacs. Doesn't use Lisp. It uses its own language. I don't know what it's even called, if it has a name, but some people use this. So Vim is, some people say Vim stands for Vim improved. I call it Vim modal. Vim is very modal. You enter states of, you insert a command and you have to, or you insert text and you start typing text. You have to leave that mode. You do a compile, you enter the compile mode, do things, and then return from the compile mode, go back to text editing, these types of things. So, like I say, I don't use Vim. I've never been able to do it, but some people are very efficient with it. So, if you're used to it, yeah, why not? I had to mention this because Roberto, one of my colleagues, bugged me about it. He uses Kate, one of the KDE editors, for doing development. Why, I don't know. Yes, it has a syntax highlighting. It has this code folding thing that you find in Microsoft as well. You can click the little minus button and it'll collapse your function down into just a single line. But it really doesn't have a lot of the other integration things. Sure, it gives you a terminal. You can build things and have a command line in it, but it doesn't integrate. You can't jump between the debugger and the code and these types of things. So I had to show it just because he said, "Oh, you have to show it. You have to show it." You know, his hands up in the air. He's Italian, so I hope nobody's getting offended. I'm not being very politically correct, am I? This is politically correct, right? If I show the KDE part, I have to show the GNOME equivalent. This is gedit. It's a lot like Kate. Does the syntax highlighting. It's extensible through a plugin interface. I believe Kate is as well. Some of the default plugins available for gedit include, again, the ability to run a command. It's just run a command. It's not proper integration. So you can't jump between code and compiler warnings, or the debugger and compiler warnings, these types of things, but something you can use. I do have quite a bit of time. So even though you think I'm done, I'm really not. I prepared a little bit of extra information just in case I went through too fast. I love to talk, and I tend to talk too fast sometimes. So extra material, always good to have. Valgrind doesn't come with just memcheck and callgrind, the profiler. It also comes with some other very handy tools. Massif, or Massif, or however you're supposed to say it, I don't know. This is a space-time memory profiler. This is a pretty neat little thing. If you find that your program is using more and more memory, but memcheck doesn't find a leak, well, Massif can give you a space-time profile. Show how much memory is my application using over time. And at any given time, during the execution, you can see how much memory was in use and the names of the functions. Wow, that's really bad. You can see which functions are actually responsible for allocating that memory that's in use. So these types of things are very useful. If you have a long-running program, you can see where is all the memory allocated, where is it freed, what's the average use, these types of things. If you find that your application doesn't perform well in low memory situations, this you can use to kind of help isolate the problem. Right? Very useful tool. Generates a PostScript graph so you can actually print it off onto paper so you can kind of mark things off and maybe go look at the code instead of having to switch back to on the screen. So I've used this a little bit before. This graph was generated by the semaphores example, but the scaling didn't turn out that well. You can't see the function names. None of those are actually cute, believe it or not. It's all the runtime linker and the C library that allocated that memory. So, shameless plug. Qt doesn't use a lot of memory. Right. There's another tool that Valgrind comes with called Valgrind. This is a data race detection program for threaded programs. It's based on a paper submitted to I think it was the ACM. I may be wrong. But what it does is it looks at the locking pattern of every thread and tries to see what data is accessed between the lock points. And then it examines what other threads are doing, and it can find, oh, that particular thread is accessing the data outside of the lock that this other thread had accessed from within a lock, or things like this. It can also detect a thread has accessed data under lock A when that thread does it with lock B. These types of things, right? Those are data races. This is what Valgrind can support. Unfortunately, it doesn't work that well with Qt 4. The people that went to the Qt in depth yesterday, and the ones, if you come to the Qt in depth later this afternoon, you'll find out that in Qt 4 we use a lot of hardware atomic instructions to do synchronization, and this doesn't work real well with Valgrind because Valgrind only supports the pthread, the POSIX thread primitives. It only supports pthread mutex lock and pthread mutex unlock. It doesn't understand that whenever I do an atomic instruction, an atomic increment, or a test set, it doesn't understand that that is actually safe. And since we implement qmutex on top of these atomic instructions, it complains just about just about everything in a Qt4 program. So it's not that useful for Qt4. If you're still using Qt3, this is a very good tool you can use. If I have the time, which never happens, unfortunately, I had hoped to maybe go in and try to help the Valgrind guys to make it work with these atomic instructions, and possibly also with the Qt4 API. That would be great. Just have to find the time and the way to do it. That's really all that I had, I promise. No surprises. Any questions? Like I said, this was not a real in-depth view. This is more an introduction. This is a way to kind of jumpstart and get you over to maybe porting and start developing on Linux.